Okay, so version 2.7 of the Tycho software was released a few days ago, and so I'm just now getting together a short video on what you can expect to find in this version, what kind of improvements you can expect to see. So to get started with on this version, it has a much simplified interface for tracking objects. In other words, there used to be, for example, a start speed, stop speed, and a step size. And those three parameters have now been consolidated into just one parameter, which dictates the maximum object speed. So it's an overall constraint on the search space, and so makes things a lot easier in that regard. The next item here is it also has the ability to automatically compute the static threshold. So you can just simply click a button and it will do the will run through an algorithm to compute it for you. The next item here is also very important. So I had determined, I found through a data set that was provided to me that it was having difficulties. Earlier versions were having difficulty detecting really fast objects, and so this has now been fixed in version 2.7, so this is certainly a nice improvement there. The next item kind of goes along with that, so I call it a line segment module, and what this does is you can simply create a line segment for streaked objects, and this allows you to run some, it'll actually run some computations for you automatically on the speed, position, angle, and so forth of the object, as well as the ability to automatically center on the midpoint. And so it's another facility for these really fast-moving objects that may produce a streak as well. And finally, the last point here is earlier versions of Tycho, you could run multiple worker nodes, so that would be one per machine. This version now also supports the ability to run multiple GPUs per machine, so that is also a nice enhancement there as well. So I'm just actually going to go ahead and go off to a demonstration now so that we can see these features in detail. Okay, so this is 2019 GN20, and this is an object that is moving at 140 arc seconds per minute with a position angle of 185 degrees. So what I'd like to start off with is this express mode. This is a new feature in version 2.7, and what it allows us to do is perform the items that have been checked in this list in one pass, essentially. So alignment, normalization, and plate solving will be performed all in one step. So as you can see, it's starting the alignment process, and so I'm going to go ahead and give that a moment. Okay, so the alignment has finished, and now it's off to do normalization, as you can see here. And now it's performing plate solving. Okay, so it looks like everything is finished, so I'm going to go ahead and close out of this window. But before I do, you can see that it has saved the output to this directory. So I'm going to go ahead and add in those files. So, and at this point, we are now ready to start the tracker. So another thing that's nice about version 2.7 is that this threshold here, you can just click this button and the program will identify an optimal value for you. So that's kind of nice. Sensitivity threshold, this is as before, giving you that flexibility to run the tracker as sensitive as you want. In this case, we can be fairly sensitive because it's a known object, so that limits the number of search vectors. So anyway, I'm going to go ahead and click OK on that setting there. And really, what's definitely nice about version 2.7 is the simplified parameters here for the tracker. So there used to be start speed, stop speed, step size. Those have all been replaced with this single parameter, max object speed. And this is, by default, it's computed by taking the image exposure time and determining what kind of speed would be the result of an object having a streak of 4 pixels across. So anyway, ordinarily you won't need to even adjust this parameter, but if you're looking for objects that have a quite a bit of trailing or some amount of streak to them, then maybe you might need to. But even in this example of this 140 arcsecond per minute object, of course these are 1 second exposures, there's no need to adjust this parameter. However, since we are performing a targeted search, in other words, we know the speed and position angle to some degree, we can go ahead and populate these parameters. So I'm going to go ahead and do that here, choosing a lower and upper bound on the speed of the object. And for the position angle, I like to give plus or minus 10 degrees, so 175 to 195. And so let's go ahead and see what that comes back with. Okay, so it finished, and yeah, I need to close out of that window. So it looks like it came back with 1 track, and that's nice. So let's make sure that this is actually the object that we're looking for. So I'm going to go ahead and load up the star catalog, and if I want to, I can go ahead and optimize the track and finally verify. So yeah, if I create 3 observations, that's fine. But I'm actually going to create just 2 because I know that the object was originally submitted with just 2 observations. So just to be on the a good comparison, since it was originally submitted with 2 observations, I'm going to do that here as well. So 2019 GN20 is the object, and so we have those 2 observations. So let's go ahead and see how it did. So we view with existing observations, and hopefully that'll bring up a maybe we don't have a good connection to Minor Planet Center. Okay, so ordinarily I would be able to select these observations and then choose this option here, which would then download all the other observations of this object. But for some reason the Minor Planet website is currently experiencing difficulties, so instead what we can do is simply view these 2 observations, and then I happen to have the text file containing the other observations already. So these are the 2 that were originally submitted, and so let's actually go ahead and take a look and see how that compares with these new observations. So I'm going to go ahead and do find orb on that. So again, these were the originally submitted observations. So as you can see, having a 3.5 residual, and so if I then replace with the new observations here and save it, then let's take a look and see what that does for us. So okay, so we now have a 3.2. So it was 3.5, now we have 3.2, so at least we didn't do any worse. Okay, so anyway, that should demonstrate that indeed we detected the object just fine. We had good measurements of the object, at least they're good in comparison to what was submitted originally, and yeah, it found the object no problem. So and it's a reasonably fast mover. So that's this particular example. Okay, so another object that I really like to take a look at is 2019 JH7. And by the way, the data for this object was provided by Northolt branch Observatories. They were kind enough to provide it to me to look at and process in Tycho. And so again, thanks to them. And what's really nice about this object, it's one of those rare ones that you come across that, for starters, it's a very fast-moving object. It's 1140 arc seconds per minute in speed, and it also, even with these very short exposures, has a noticeable streak to it, so a bit of trailing. So that's the question, is whether or not Tycho can actually detect this kind of object. So, and of course, if it can, then how good are the measurements? So let's go ahead and load up these images. And again, we can perform this express mode. So we're going to do alignment, normalization, and plate solving. Okay, so now we are ready to run the tracker. So let's go ahead and run through these steps. Again, we have the option of either specifying this setting manually, or we can click auto threshold. So I'm going to let the program do it for me. And sensitivity threshold, again, I'm just going to use 10 for this example. And however, on this page here, max object speed, because this is a streaked object, we do need to actually specify a faster speed here. So it's around 1130, 1160 arc seconds per minute. So I'm just going to be on the safe side and choose 1200 as the max upper limit. And I already put in the lower and upper bounds here. So 1130, 1160 for speed, and I did plus or minus 10 degrees in the position angle. So let's go ahead and see. This is 4500 vectors just about. So let's go ahead and see how it performs with those settings. And I'm actually just going to go ahead and let it run through this whole recording just so you can see how long does it take Tycho to process these 4500 vectors for this particular data set. Again, there's 125 images here. So it's actually very quick. And of course you'd expect that because we put in limits on the speed and position angle. So this is kind of nice. This is the object in question. And so let's go ahead and load up the star catalog here. And let's also go ahead and optimize the track and verify. So I'm going to give 3 observations here because that's how many were originally submitted. So give it a designation, and then it comes back with these observations. So Minor Planet website, I believe, is still down, so I cannot use this option here, this functionality, because it's not going to be able to download existing observations. However, I do have the text file that I downloaded once before. It's been archived, so I can still use that. So I'm going to go ahead and view these observations. Oh, and by the way, what I had to do to get this data set to work with Tycho, the exposure times actually referred to end of exposure. Again, that's unique to this particular data set. Most people would use this option here, but I did have to, for this data set, use timestamp refers to end of exposure. Anyway, and of course, the setting here, the observatory code is Z80. So, all right, let's go ahead and take these observations that were generated on this object and plug them into the Find Orb software. Now, before I do that, what I'm going to do is I'm actually going to, we'll see how the original observations performed, if you will. So let's see if I actually have a copy of that or not, because I did make a slight change. So this is the original file here. So hopefully I can do that. I'm going to save this in DOS mode so I can use Notepad and save that. Alright, so just bear with me for one moment. Okay, so here is the original file of observations that were submitted, and I'm just going to single out all of the observations made by Z80. So anyhow, the time frame we're looking at is here. So 0.940 it's 0.941. So these are the original observations, and so let's go ahead and run that through the Find Orb program and see what kind of residuals we had with these original measurements. So Okay, here we go. So 941. So 2.5 is the error on the arcsecond here. So on that 941 measurement. So we'll compare these auto-generated measurements with that. So again, it's a streaked object, so hopefully it does well. But again, can't really be 100% positive on that. If it can really find that centroid very easily on its own. So 940, 941. So actually, yeah, it's kind of not so good. So 3.8. I mean, it did find the object correctly. This is the object for sure. But 3.8 is not a particularly good residual. So let's see if we can actually improve upon that through a bit of manual tweaking of the measurement. So let's go ahead and take a look and see. Again, this is another nice thing about version 2.7 is it makes it easier to make manual adjustments of measurements. So I can right-click on the object and click Modify Observation. And so I can also use these buttons here to make very precise pixel adjustments. So, and also there is the a line segment tool. So if I wanted to, it's not really necessary for this object because it's not a huge streak, but if I wanted to, I could navigate to kind of the start of the object and then do the same for the end point of the object. So that gives me a line, and I can click here to go to the center of the object and then say, okay, let's use that as the centroid. So anyway, that has now updated the first observation. I can do the same thing for the second one, which of course has, it's certainly could use improvement. So let's try that right here. And finally, this third measurement here, we can also modify it as well. So hopefully what I'm doing here is actually improving the residuals. I won't know until I actually try it and find orb, but let's go ahead and take a look and see what that does for us. So again, these are the observations. So I'm going to save that, and let's see what find orb thinks of this modification. So here we have 940.940.1. So these are the new observations, the new measurements that I just made. If we compare that, so 9403 and 9408 and 9413 right here. So these also line up 4, 3, and 9 on that. So looks to me like the worst residual is 0.85. So that compares favorably with what was originally submitted as having 2.5 as a error in residual. So anyhow, this is a very fast mover, 1140 arc seconds per minute. In fact, what we can do, it displays that in this notation. So a very fast moving object, and nevertheless, Tycho was able to identify it very quickly, and through some manual guidance on the measurements, it was also able to give very nice residuals as well. So that's it for this example. Okay, so what I would like to demonstrate now is the ability to distribute workloads across multiple GPUs for each machine. In other words, previous versions of Tycho had the option of allowing you to distribute workloads across multiple machines, but you could only have one GPU supported for each machine. This is now improved in version 2.7, whereby you can now distribute the workload across multiple GPUs for each machine. So in this example, I have two machines here. So this connection and the one over here, and each of these machines has got 8 GPUs. So we're going to be able to distribute a workload across 16 GPUs total. So let's go ahead and take a look and see what that looks like. So the first thing we have to do is specify for each machine what worker nodes are to be assigned. So you can think of a worker node as being an instance of Tycho. So here what we have again are these 8 GPUs, and what I can do is assign a port number for each of them. So, and I'll just go ahead and do that here real quickly. And these are Tesla V100 GPUs, by the way. They're actually kind of not very good value for the performance that you get out of them. If I were to do this in the actual production environment, or if I were to do this in any kind of scenario where I wanted the most value per performance, I would use an RTX 2080 GPU, which are far more cost effective. But these will suffice for this demonstration, and the only reason I'm using them in the first place is because they're the only GPUs available from the service provider I have here. But anyway, for this example, again, we have 8 GPUs on this machine, and you can also look at command line syntax. So if you were to start these instances from the command line, this is how you could do it as an example. So you would launch Tycho with these command line arguments. So anyway, what I'm going to do is, I might as well just copy that to a batch file. So I can copy and create a new batch file here. So let's see, might as well give it a more meaningful name. So anyway, if I copy those commands into a script, and of course, and this view that I have here, it is hiding the extension. So let me go ahead and fix that. Okay. All right, so this is now a proper batch file. So if I were to double click, then you'll notice that it starts 8 instances of the Tycho software, 1 for each GPU. All right, fair enough. So that being the case, we now have this machine configured properly. And so let's go ahead and go on to the next machine. Okay, so now over on this machine, again, I have another 8 GPUs to configure. So it's going to populate the list. So that takes a moment with these drivers here. So okay, again, so I used up to 4507. Anyway, I'll just do 4510 as the start here. So again, this is just initial configuration. Obviously, you wouldn't have to do this each time, but I'm showing it here in this example just to show what the process is like. Okay, so again, I can create a script for this if I wanted to, but on this machine, I'm actually going to use this as the primary controlling node, if you will. So, so I really actually don't have to launch them on this because it's the primary node. So what I do need to do, however, is set up the cluster. So what we can do here is give each node a name. So I'll start with the letter A for the first machine and work from there. So localhost and 4510, and I'll just continue on with this. Okay, so having done that, we should be able to ping all of these worker nodes. And so as you can see, we get a response back. Of course, I haven't started them on this machine here. So okay, I might as well do so. So I can just launch them using that command. And so if I ping now, then I should get a response back. Okay, so now we have all 16 GPUs running, and so what I'd like to do with that is let's go ahead and run a data set through this through this interface. Okay, so before I start the processing, I'd like to go ahead and just point out the data set here. This is 2019 GM20, and so these are 10-second exposures, of which there are 213 of them, so it's about 35 minutes total elapsed time between taking all the images and any interval elapsed between them. So the question is, this object, again, this is 2019 GM20, which is it's different than the one I had earlier, 2019 GN20. So this one is an object moving at 16 arc seconds per minute, and the question is, can we detect not only the fast mover, but also the slower moving objects as well that are present in the field of view. So again, earlier versions of Tycho, you used to have to have a certain amount of time elapsed from one frame to the next for a slower moving object to be detected. So now, as you can see with these being 10-second exposures, you certainly, with those previous versions of Tycho, you would not have been able to detect those slow movers, but now with certain improvements that have been made, now we can. So it's a lot of images, and certainly going to be a lot of motion vectors to search over, because of the fact that we are searching from all the very slow moving objects all the way up to the fast mover at 16 arc seconds per minute. So this results in about 200,000 motion vectors. And so it's a good exercise for this example, because now we can also apply the use of multiple GPUs as well to distribute the workload. Okay, so I have a script here just to show you what it looks like. It's very simple. So we are going to launch Tycho in auto run mode and operate on this data set. So if we wanted to, we could launch this from the command line, or I can simply double click on the script, and as you can see, it loads up the images in that data set, and then because it knows the cluster configuration, it proceeds to automatically distribute the data set as well. So very easy, very quick to do that, and it's all automatic. And as you can see, it is now in progress. So each worker node, again, of which there are 16, is now processing the data. So again, I'll point out, on a single machine with one GPU, typically would take about 7 hours, thereabouts. So while this is going to be much quicker than that, I'm still, it won't record for however long it actually will take, probably 20 minutes, 30 minutes at most, perhaps. But anyhow, as you can see, it's already 1% complete, and so that bodes well for the performance gain that we are seeing with this cluster configuration, already at 2% now. Okay, so it's been maybe 7-8 minutes, and each worker node is about 80% complete. So it's certainly coming along quite nicely, and this certainly indicates that things are significantly sped up, distributing across these multiple worker nodes. In fact, now you can start to see several of them are finishing up. So let's take a look and see how much longer it will take. Okay, one more remaining. Okay, so it looks like any moment now we should be getting the results back. Okay, there it goes. Alright, so now as you can see, it's downloading the results from each worker node. And there we have it. So we now have the results of processing that data set. So let's go over here, and as you can see, total of 619 seconds, and so that's actually pretty good for this particular data set. Again, about 6 or 7 hours on a single machine with one GPU, so significant improvement. Again, these are different GPUs than the RTX 2080 that I was using, but that is still certainly indicating a noticeable improvement. So, which detections matched up with an actual asteroid. So, so it looks like these first 5 tracks here are actually, again, these would be your slow-moving objects, and so you can see that here. And the other thing I want to do is bring this over here so I can animate from one frame to the next as well. So you can kind of see that I'm on a remote connection, so it's maybe not the best, but yeah. So you can see that here fairly well. So this would be, again, an example of one of the slow movers. So it detected that just fine. Let's look at another one just at random here. Okay, and that one is detected fine as well. All right, so it detects the slow movers just fine. Now the question is, did it also detect the NEO object, the Northolt object that was moving at 16? So looks like we had a few false detections just right here, as you can kind of see that in this window with the horizontal line. So it doesn't look too realistic to me, but the one that is what we're after is here, so the 16 arcseconds per minute. So it did detect that object, and so just to show you that detection, again, it's a fairly faint detection. Of course, that's why we use synthetic tracking. So you can see it here fairly well. Yeah, there's some kind of optical, maybe not a very flat field here. That's why, or at least there's some kind of gradient, but that's just in the images that were taken. Anyway, so I think this is actually pretty cool because it's a very faint object for the most part. I mean, you know, signal to noise ratio. So you do have to use a stacked approach in order to detect the object. It's certainly not visible on individual frames. So if I zoom out, yeah, there's no way you would detect this on individual frames at all. So stacking is of course necessary to see the object. I mean, we can even barely see it when I stack, you know, this many frames, and you can maybe kind of start to see it. So yeah, it's a very it's a very good example, I think, because it shows that Tycho can detect the very fast-moving objects as well as the slow-moving objects in one pass. So you can use the same data set and still detect both fast movers and slow moving objects too. So I think it's pretty cool, and it did it again in about 10 minutes. So that's actually faster. 10 minutes if you consider the fact that it took 35 minutes to capture these images. If I can move those windows out of the way. So total elapsed time here in this column, as you can see, so 37 minutes actually. So 37 minutes to take these 213 10-second exposures versus 10 minutes approximately to process and identify through blind detection of both slow-moving objects as well as our NEO as well. So and it does a very good job also of ranking the detections. It does so by quality is an attribute that it computes for each track. So yeah, it does have a few false detections here, but that's not too surprising considering the number of motion vectors that it iterated over. Okay, so one more example here. This one is kind of interesting. This is the data set that I provide with the Tycho user guide, and it generally takes about 5 to 10 minutes to process, doing a blind search as well. And you might ask, well, what's the rationale? What's the reason behind, why does that take 5 to 10 minutes versus the 2019 GM20 data set took about 7 hours on a single GPU? And that just comes down to the fact that, for one, the number of images, this one has about 60 images versus this one has 213. And also the noise level of the camera. So sensitivity threshold versus noise. So the more noise, the more likely to declare a candidate detection, which in and of itself will result in more processing time. So that explains some of the differences that you would observe in processing time from one data set to the next. But anyway, in this example, again, this is one that takes about 5 to 10 minutes to process on a single GPU. So let's just, why not see how long it takes, and again, in this cluster configuration. So we're going to run Tycho on this data set. So again, you could do this from the command line if you wanted to, or from the script. And anyway, so let's go ahead and see what that looks like. Okay, so it's loading the images and distributing across the worker nodes. And so as you can see, it's starting the processing now. Okay, so that was pretty quick, as we would expect. Now download the data, the results of the data. And so if we were to compare with the MPC orbital database, we can see what objects have been identified here. So again, these are the same results that you would see, 33 tracks, if you were to follow along in the user guide. So anyhow, so very, very quick, 40 seconds. Very nice to see that result. 1.02 E15 vector pixels per hour, so that's very, very fast. So pretty neat, I think. So it does identify these objects, and so anyhow, that's version 2.7 with this capability to perform distributed processing in that fashion. So, all right, well, thanks for watching, and see you next time.